Right now, you exist. That sentence sounds obvious. Trivial, even. But the moment you understand what physics says should have happened at the beginning of everything, the fact that you are here, reading this, breathing, thinking, becomes one of the most astonishing mysteries in all of science. The universe should not exist. Not in the way a bridge shouldn't exist if the engineers made a mistake. In the deepest, most fundamental way that physics knows how to describe, the universe, all of it, every atom, every star, every galaxy, every thought you have ever had, should have been canceled out before it ever began. And yet here it is. Here you are. So what went wrong? Or what went impossibly, miraculously right? To understand this, you have to go back. Not to last year. Not to the beginning of human history. You have to go back 13.8 billion years, to a moment so extreme that every law of physics you learned in school begins to break down. The Big Bang. The moment everything came from nothing. Here is what the standard model of particle physics, the most tested, most accurate theory in all of science, tells you happened. When the universe was born, energy crystallized into matter. Particles appeared from pure heat and light. But the same equations that describe this process also predict something else with equal certainty. For every particle of matter created, an identical particle of antimatter should have been created alongside it. Matter and antimatter, two sides of the same equation, born in equal amounts. And when matter and antimatter meet, they annihilate each other completely. No explosion, no debris, just pure energy radiating outward. Gone. This is not speculation. You can watch it happen in a particle accelerator today. Physicists like Paul Dirac predicted antimatter mathematically in 1928, before anyone had ever seen it. Carl Anderson confirmed it in 1932 when he found the first anti-electron, the positron, in a cloud chamber. The physics is solid. The math is airtight. So if equal amounts of matter and antimatter were created at the Big Bang, they should have found each other. Every particle, every antiparticle. A perfect, complete annihilation. And what would be left? Nothing. A cold, empty universe filled only with light, expanding forever through absolute darkness. No stars, no planets, no chemistry, no life. And yet, here you are. Something interrupted that annihilation. Something tipped the scales. For reasons that science is still actively hunting, slightly more matter was created than antimatter. Not twice as much. Not even close. For every 1 billion antiparticles, there were 1,000,000,001 particles of matter. A difference of 1 part in a billion. That single extra particle, that tiny, almost invisible imbalance, is everything. Every galaxy, every sun, every ocean, every molecule of oxygen in your lungs right now. All of it descended from that fractional excess, that rounding error in the universe's arithmetic. This asymmetry has a name. Scientists call it baryogenesis, the process by which matter came to dominate over antimatter. And the honest truth is this: nobody fully knows why it happened. Andrei Sakharov, the Soviet physicist who first outlined the conditions necessary for baryogenesis to occur, proposed in 1967 that 3 specific physical conditions had to be met for the matter-antimatter imbalance to arise. His conditions have been confirmed as necessary. But the standard model of physics, even in its most complete form, does not generate enough asymmetry to explain what you see when you look at the night sky. The imbalance the standard model predicts is far too small to produce the universe you are living in, which means something is missing from your understanding of reality. There is a concept in physics called CP violation, a subtle difference in the way matter and antimatter behave under certain conditions. Researchers at CERN's LHCb experiment have been measuring CP violation for years, hunting for the hidden mechanism that could have amplified that tiny imbalance at the beginning of time. In 2019, the LHCb collaboration published results showing CP violation in particles called d mesons, a first. It was a crack in the door, but still not enough to explain the scale of what you see around you. The gap remains. The question remains. And it deepens when you look at what else the universe is made of. You have probably heard of dark matter, the invisible substance that makes up roughly 27% of the total energy content of the universe. You cannot see it. You cannot touch it. No particle detector on Earth has ever directly caught one. But you know it is there because of what it does to galaxies, bending light, holding spiral arms together, shaping the cosmic web of structure you see when you map the universe at its largest scales. Here is the thing about dark matter that most people miss. It is not just an addition to the story. It is another piece of evidence that your current physics is incomplete. Every model physicists have built to explain baryogenesis, to explain why matter 1, also has to account for dark matter. And the two problems might be connected in ways that are not yet understood. Fritz Zwicky was the first to notice something was wrong, back in 1933, when he observed that galaxies in the Coma cluster were moving too fast to be held together by the visible matter alone. Vera Rubin confirmed it decades later with her careful measurements of galactic rotation curves. The math did not work unless there was far more mass present than anyone could see. So now picture the full inventory of your universe. 5% ordinary matter, atoms, molecules, everything you have ever touched or tasted or seen. 27% dark matter, invisible and unknown. And 68% dark energy, the even more mysterious force that is accelerating the expansion of the universe outward at an ever-increasing rate. 95% of the universe is made of things you cannot directly detect. You are living inside a cosmos that is almost entirely unknown. And yet, even that is not the strangest part. The strangest part is what quantum field theory tells you about the vacuum of empty space. In physics, a vacuum is never truly empty. At the quantum level, space itself is seething with energy, virtual particles flickering in and out of existence billions of times per second, borrowing energy from nothing and paying it back before anyone can notice. This is not a theoretical curiosity. It is measurable. The Casimir effect, the tiny attractive force between two uncharged metal plates placed extremely close together in a vacuum, is a direct measurement of this quantum energy. But here is where the story turns vertiginous. When physicists calculate how much energy the quantum vacuum should contain, using the same equations that have been verified in every other context, they get a number. And when they compare that number to the actual measured energy density of the universe, the prediction is off. Not slightly off. Not off by a factor of 10, or 100, or 1,000,000. Off by a factor of 10 to the power of 120. That is a 1 followed by 120 zeros. This discrepancy is called the cosmological constant problem, and it is widely regarded as the worst prediction in the history of physics. If the quantum vacuum contained the energy that theory predicts, the universe would have been torn apart instantly at the moment of its birth, expanding so fast that not a single atom could ever have formed. The fact that matter clumped together, that galaxies grew, that stars ignited, all of that required the vacuum energy to be almost perfectly, impossibly zero. Not exactly zero, but tuned to within a fraction of a fraction of a fraction of what it theoretically should be. Some physicists invoke the anthropic principle here, the idea that you can only observe a universe compatible with your own existence. So, of course, you find yourself in one where the constants allowed life. But that answer sits uneasily with many. It feels less like an explanation and more like an admission that the explanation has not yet been found. Others point to the multiverse, the idea that your universe is one of an enormous number of possible universes, each with different physical constants, and you happen to live in one where the numbers worked out. String theory offers a landscape of perhaps 10 to the power of 500 possible universes. But no one has yet found a way to test this idea. A theory that cannot be tested is not yet science. It is a hypothesis waiting for its experiment. And so here is where you stand. The universe should not exist. The physics that describes it most accurately also predicts its own annihilation at the moment of its creation. The matter you are made of should have been erased by antimatter in the first second of time. The vacuum should have torn space apart before a single hydrogen atom could form. The structures you see when you look at the night sky required a kind of cosmic fine-tuning that no current theory can fully explain. And yet, stars burn, planets orbit, life arose, you exist. The most honest answer that science can give you today is not a solution. It is a direction. The standard model is not the final word. Dark matter and dark energy point toward physics that has not yet been written. Baryogenesis points toward a symmetry-breaking mechanism that experiments have not yet isolated. The cosmological constant problem points toward a deeper understanding of space, time, and the quantum vacuum that is still being built. You are alive at the moment in history when humanity is pushing hardest against these questions. The Large Hadron Collider, the James Webb Space Telescope, the Event Horizon Telescope. These are not just instruments. They are attempts to find the missing piece, the explanation for why everything that should have been nothing decided, against all physical odds, to become something instead. Tonight, look up. Every point of light you see is a star that should not exist, burning in a galaxy that physics says should have been annihilated before it ever formed. In a universe whose survival defies the most precise equations your species has ever written. Right now, you exist. And that is the most extraordinary fact in the known universe.